Good morning. So today, in fact, we'll be continuing discussion on this dynamic shift register, and also we'll discuss a little bit about the precharged logic, nMOS, and as well as CMOS, if time permits. Let me refer back to the discussions held in the last class. I was discussing the ratioed logic with a clocking scheme which is different from the earlier one discussed in the same class, in the last class. The difference between this shift register and the one discussed just before that, you see that here the two clocks simultaneously turns on and off both the pass transistor and the load transistor in each stage. So this is more or less these are the so-called inverter stages, and the pass transistor of each stage and the corresponding load transistor is operated by the same clock. But earlier case, you remember that this transistor was kept either in saturation or in depletion mode, whatever you like. But in this case, it is not permitted to do so. The advantage of this particular configuration is therefore that we don't allow this transistor to turn on for a long time, because usually the clock duration is small compared to the clock period. How to choose the clock duration, the pulse width of the clock, and the pulse repetition frequency or repetition rate? I'm sure you understand what are the criteria for that. For example, how to choose the pulse duration? You have to allow sufficient time so that the potential is built up properly. That means steady state is achieved at the respective nodes. That means charging is completed. Otherwise, what will happen? You will get less swing. In order that there is full logic swing, so that this device, this circuit is less immune to noise, external noise, we must choose duration, the width of the pulses sufficient to allow full charging of the capacitors at the corresponding nodes, for example, A, B, B dash, C, etc. All right, this is how to choose the value of the pulse width or clock duration. Whereas the period is determined by applications. The pulse rate, the clocking rate depends on the application. This circuit will not work below a certain clocking rate. I'm sure you understand. If you allow too much time, then the charge at the corresponding nodal nodes will not be retained, and as a result, the circuit will malfunction. So in order that the circuit functions properly, we must choose the period of the clock pulses or the repetition rate properly. In that case, one can easily say that it should be above a certain minimum value. And how to get that value? In fact, that analysis we are not doing in this class. But if you remember something I did in connection with the transient analysis of the MOS inverter, the same analysis is applicable to determine, if you like, the similar kind of equations. The same way we advanced, we did the analysis exactly. All those methods are applicable here to determine what is the minimum clock rate needed for the proper functioning of these devices. Similarly, you can also find out what is the minimum pulse duration needed for the proper functioning of this circuit. This is one thing. Now let us come back to this particular circuit. This particular circuit, as mentioned earlier, has got a little bit different clocking scheme. Earlier, only these switches were operated by the clocks, but now we have also included the load transistors, simply to reduce the power dissipation. That was the main motivating factor for doing so. In order to do so, what I have to do? Naturally, the clocks now have to drive more capacitance, because earlier it was per line, per row, only one transistor. Now there are two transistors. So naturally, the clock pulses have to drive more charge. So the load on the clocks will be more in this particular case. You have to have, you know that you have to have a clock generator. We have to have clock generators, in this case two-phase clock generators with proper driving capability. That has to be noted. Here, the drivability of the clock pulses should be more than in the earlier configuration. Now, what I was trying, I think you tried this and you have also seen that how it works. Let me repeat once again. Now, particularly, I am interested to see why these things are happening. You have noted at the point B and B dashed, at the point B and C particularly, you find some small kinks at certain locations in time. Why these kinks? That has to be understood. Are they desirable? If they are not desirable, what to do? These points have to be discussed. Why the kinks? Particularly in the B waveform, why the kink? You see that at this particular instant of time, A is low. The voltage here is 0. Therefore, this transistor is supposed to be off. And therefore, this transistor will be on only when phi 1 is high. Otherwise, it is not on. So you just see before this particular instant, this was charged to a certain voltage, and because it was off, that is why the B was in the high state. It was charged to the full voltage, in this case, of course, not full voltage, minus Vt. At that particular point, from this time to this time, you know, from this instant to this instant, both phi 1 and phi 2 are 0. So both the transistors are off. So whatever voltage was there in this node, so both this transistor and this transistor, both of them are off. So whatever voltage was there, that will be retained for that, and that was exactly what happened from this time to this time. Then at this particular instant, you see that phi 1 is 0. That means this transistor is off, but phi 2 is high. That means this transistor is on. So what will happen now? There will be charge, this charge, whatever was there, will now flow towards the point B dashed. As a result, at this point, the charge will be less and voltage will fall because there is nobody to replenish that charge with this transistor remaining off. You see that from this time to this time, this transistor is off, whereas for a very short duration here, this transistor is on. So whatever charge was there, that was redistributed, resulting in a slightly lower voltage, and that will continue up till the next pulse comes. Next phi 1, the next pulse, that means next phi 1 clock comes. At this instant, what is happening? Again, A goes high, and in spite of the fact that this is on, does not matter, because in this case, this is high and this is high, means this transistor is effectively remaining in saturation region. Both are 5 volts, and this is on because A is high now. So whatever charge was there will now discharge quickly. I have not shown anywhere the charging and discharging time. In fact, I have shown everywhere sharp fall and sharpening. It is actually a very simplistic diagram. Let me tell you that this timing waveforms, whenever we draw, we usually do not show that so-called charging and discharging time, on and off times. But these are very important. Always you'll find the signals will be a little bit delaying with respect to the clock because of the delays which are involved in the data path. Okay, that has to be remembered. But we have not shown it here intentionally. There is no harm. You can include it there. And you see that then from this instant to this instant, A is continuously high. That is, this transistor is on. B, whether this transistor is on and off, whether this transistor is on and off does not matter. This potential will remain zero because it is offering a very low resistance path. And that is why from this instant to this instant, it has remained 0. And again, there is a change here. Exactly the same thing has happened at this instant when phi 2 is high. Exactly the same thing, and that has resulted into this kind of thing. This kink will be high. When, how to? I think I'm sure that you'll appreciate that these kinks are not desirable. Should there be how to reduce these kinks, these sudden depressions? How to reduce these kinks? Yeah, please.
By reducing the clock duration.
Again, if you reduce the clock duration, then the problem of full charging, that clock duration should be such that the charging is full. That is very important. Actually, I want that the capacitance, when this is off, the effective capacitance between B and ground should be quite large compared to the effective capacitance between B dash and ground. Is it all right or not? Because if I have a large capacitance here, it holds a lot of charge when it is fully charged to VDD. And even if it loses a little charge, its voltage does not drop appreciably. Because if this capacitance is small, for the same voltage it will store less charge. And this capacitance is large, means for the same voltage it will store large charge, very large charge, a large quantity of charge. So in that case, when phi 2 is on for a short time, there will be charge, that this thing happens very quickly. This thing happens very quickly. So what will happen now? This charge distribution, but it loses only a small charge to fill up the capacitance properly. That means to charge this capacitance to the proper final voltage. So naturally, as a result, the voltage at this point will not fall much. At this point, I'm not speaking of the point at B dash, but at this point B will not fall much if I can maintain the condition that the capacitance at the node B with respect to ground is large compared to the capacitance at the node B dash with respect to ground when this transistor is off. Now please see that. What are the effective capacitances coming between, suppose when this is off means drain bias may be there, but the gate bias here is 0 or less than threshold voltage. That is how we call it an off transistor. At this point, therefore, there is a MOS capacitance between the gate and substrate of this transistor, substrate and source. Please remember, all the substrate is shorted to ground. Please remember that. So between the source substrate and the gate, there is a capacitance, which is the MOS capacitance. And I have also a capacitance between the drain and substrate of this transistor, which is reverse biased, usually reverse biased, maybe 0 bias to reverse bias, any certain range. Whenever, if this voltage is high, then it is reverse biased, but if this voltage is low, that means it is not biased. But then this capacitance, there is a capacitance, a junction capacitance between the drain and the substrate of this MOSFET. So there are two capacitances in. One is this one, and remember that the substrate is all the transistor, substrate is grounded. All the transistors, this is built on a P silicon substrate, and this P silicon substrate is grounded. Please remember this. And therefore, these two capacitors coupled, added together will be the total capacitance at this point. And what about this? What about this? Here the predominant, most important capacitance is this capacitance between the leakage capacitance, or the capacitance between the R and when this transistor is off. I am speaking when this transistor, when A is low, that means when this transistor is off. What is the capacitance at the node B with respect to ground? What is the capacitance? It is simply the junction capacitance of the drain substrate junction of this transistor. Am I correct? Now let us see the geometry. In order, because it is a ratioed design, you remember the geometry of this transistor has to be, the W by L of this should be quite large compared to the W by L of this. Already, therefore, the area of the junction, the drain junction at this of this transistor will be higher, quite high. Of course, much higher than this transistor. What about this transistor? This is similar. But here, at this point, the capacitance between the drain and substrate does not come. Of this transistor, it is only the MOS capacitance. This extra capacitance is not there, but we have the extra capacitance between the drain and substrate of this transistor. Usually, these transistors are not that large. The pass transistors are not that large. And as a result, it is not unusual to maintain the condition that the capacitance at the node B large compared to the capacitance at the node B dash. It is more or less automatically satisfied because of the ratioed logic which we have used to implement this circuit. But please remember, there will be some fall. There will be some fall. Our purpose, our design methodology should be such that these kinks are minimized. That means this kink must not fall below what? The unity gain point. That means below the noise margin, the high state. Okay? So that has to be kept. So that is a design criteria, and if I want to do that thing with some mathematical analysis, then I have to write down all those equations, and I have to consider that into account so that this particular criterion is satisfied. Exactly the same thing has happened at the point C, because B and C are analogous. Only thing I think I have made a mistake, and let me make that correction. At this point, there will be, what will happen really, you just see that now, so far as this transistor is concerned, at this node is concerned, at this instant, when phi 1 is high, this transistor is on, there has been a fall. Am I correct? At this instant, when phi 1 is high, that means this transistor is on, there has been a fall. It is as expected. Then, at this instant, what is going to happen, which I have not shown? At this instant, what is going to happen? Because at this instant, you see that phi 2 is on, but phi 1 is off. That means this transistor is off, this transistor is on. So again, some charge will flow in, and it will rise. So this is wrong. This portion is wrong. It will rise. It will remain like this. Then again, there will be a fall. So these things are to be erased. So it will be something like this. This. Please remember, this is the correction which I should want to incorporate here. These are wrong. This is wrong. All right? So you see that, and as a result, finally you can see there is a 1 bit. It is a bit typically a shift register, dynamic shift register. The advantage of this shift register as compared to the last circuit is that it gives you less power dissipation. The power dissipation here is much less, and as a result, power delay product also will be less, considerably less in this particular case.
So there should be another fall when beginning of C.
At the beginning of? At which point you are saying? Oh, acha, yeah. At this point, which I think I will show. Oh, I see. I think this is for, I think by mistake I have shown. This should be at this instant there is a fall, then rise, then kind of thing. Am I correct? Yeah. See nothing. What I wanted to say that this portion I have not really taken, I have not plotted seriously. Just I started with some one letter. Same thing is going to happen. You can easily understand. Now consider a design which is called ratio-less design. Two-phase ratio-less shift register. This circuit is quite interesting. You see that here, in this particular case, it is totally different from the conventional one. I have not applied any so-called power supply. VDD and ground is missing. You just see that there is no VDD point, no ground. But then how it works, that has to be seen. You see the substrate is ground. Substrate is ground, and any clock signal means, these are signals are called unbalanced signal. I think you have heard, this terminology. Say power supply, sometimes power supply is floating. That means both plus and minus, none of them is ground. But certain power supplies are one terminal is always ground. Any electronic instrument, measuring instrument, always one terminal is ground, the other terminal is off ground. Why? Even for any high frequency setup, you'll find a signal generator also. You get signal through a BNC connector. One terminal is ground, the sheet, the body. The other terminal is off ground. Measuring instrument, as you put a BNC connector, you find that the sheet, the outer connector, is ground. Only the inner core is non-ground, off ground. Why? For noise point of view, I think you know that. These are called unbalanced instruments. Unbalanced in the sense that it is not a balance. Both the inputs, both the points are not at the same potential with respect to ground. If you take a transformer, suppose I have got a power supply where one side is ground, the other side is non-ground. I want to convert it into a power supply where both the points are AC line I'm speaking of, then not DC, AC. Then what I have to do? Simply you just pass it through a transformer. Secondary will give both points are floating. I think those techniques are very well known to you. In our supply line, the neutral is not ground sometimes, but it is the generator is so designed that neutral has got a very low potential, practically at ground. I think you know that the line, neutral, three-phase supply, etc. Similarly, any clock, whatever you generate, usually one terminal will be ground, the other terminal is off ground. So phi 1, phi 2, whatever clock signal I have shown, these are pulses rising from 0 volt to a positive voltage, positive going pulses. And please remember, our substrate is grounded. That there is a ground, it is not a floating one. The chip is not floating. The substrate is grounded. Please remember, the substrate is grounded. And instead of applying any power supply anywhere, I am managing everything through using clocks only. That is to be understood. Naturally, you understand this will increase the load to the clock supplies, clock generators. These clock generators are entirely different from the kind of clock generators which you have used earlier, because we had to drive only the gates. In the earlier examples, you see that the clocks were driving only the gates. It was not driving any drain current. But now in this case, it has also to drive drain current. Therefore, the driving capability of the clock generators in this particular example should be much higher. This is one thing. Another thing, you see that, do you think that these are inverters? No, because in the case of inverter, this is 1 voltage is another, ground and VDD, or something like that. But here you see that both the terminals are raised to phi 1. Both the terminals, both these sides are raised to phi 2, then phi 1, phi 2, etc., etc. So these are not inverter. So this is not, that is why this is what is called ratio-less shift resistor. Because these are not inverters. This is not an inverter, this is not an inverter. These are all independent switches. All these MOSFETs are independent switches. Therefore, there is no need, I shall discuss, there is no need of doing the ratio design. Maintaining the ratio of the W/L ratio of the drive transistor with respect to the load, that thing has not to be maintained. But there is some other criteria, we shall be discussing that. Let us see how this circuit functions. You can try yourself. We consider again the clock pulses first, as before. You try yourself. This kind of diagram we always find in microprocessor or any system, the timing diagram they supply. So these are very similar. These are nothing but that same thing. So this is my input. So this is like this 1 0 1 1 0 0 1 type signal. We now show the voltages at different points. For example, the point A, it can be drawn in the same way as we did earlier. At the point A, it will be in synchronization with phi 1. So if I assume that it remains the same at the same state, then this is just as we have drawn earlier. In the point B, you look at the diagram and see what is happening. So see that at this particular instant of time, A is high. From this point to this instant, A is high. So A is high means this transistor is gate voltage is high. Now when phi 1 is 0, means the gate to source voltage is high, then this transistor is on. Please remember that this has to be, this transistor, their source and drain interchange. Kind of thing, you just see that when phi 1 is 0 and A is 0, A is high, then you consider this side as source and this is gate, this transistor is on, very heavily on. It may remain in saturation or in linear region depending on what is the voltage at this point with respect to this. Okay? When A is high and phi 1 is also high, you see that you can consider this transistor as if that this side is drain and this side is gate. Depending on this point, this will be always less than high, that 5 volt. So this transistor will remain on. Saturation or linear depending on what is the voltage between this point and this point. Please remember, this is a very important thing. When phi 1 is high and A is high, as if this transistor is, this side has become drain and this side has become source. Suppose this goes, there is no negative voltage anywhere. All the voltages are changing from 0 volt to 5 volt. High means phi 1 is phi, towards phi kind of thing. So what will happen, this transistor therefore will be on. when A is high, phi 1 is 0 or 1. But when A is 0, is low, then when phi 1 is 0, naturally it is off. And when phi 1 is high, then also it is off, because you can consider as drain. It is also off. So A0 means this transistor is off. What about this one? You just see that when phi 1 is high, both the drain and source, drain and gate, they are the same potential. This transistor is on and in saturation. Because, am I correct? When phi 1 is high, this transistor is on and is in saturation. And when phi 1 is 0, this is off, because the potential, this is 0, and the whole potential difference between this to this is, you have kept as if this has become drain and this has become source. And this turns off. Source drain of each transistor as if they change their role. Sometimes this side is behaving as source, sometimes this side is behaving as drain and as source, and vice versa. So this is happening for both the transistors. That is why, please remember that these are not conventional inverters. These are all independent switches which are turned on and off by suitable pulsing or clocking. All right. So in that case, you see that A signal, as you apply an input like this, at the point A, you can connect. It is the same thing as before. You can draw the waveform at A as usual. Then you have to draw now the waveform at B. How to draw it? How to draw it? I'm drawing, you just check. Next pulse. These are a little bit you just see what is happening. Very difficult for me, because you cannot show that both the things simultaneously because of my limitation. I think you can see it, okay? You can see it. Now, I think you understand that at this point what is happening? Phi 1 is A is making a transition from, say, before that A is high. A is high. Now before that, before this instant A is high, and for most of the time phi 1 and phi 2 are 0. Before this point, A is high, and as a result, what is going to happen? This B will be at 0, because this whatever voltage charge was there when phi 1 was 0, it will discharge. So this point will remain in 0 potential. Then at this instant, when I come to this edge, when phi 1 is again high, then you see that A already has made a transition from high to low. But now phi 1 is high means what is happening? This transistor is on, and this is also on or off? No, at this point A is 0. Please remember that. No, sorry. Yeah, at this point A has become 0, so this transistor is off, though phi 1 is high. So what is happening? In this case, through this path, the node B will be charged, and as a result, it will go towards that high voltage. at this point. This will continue till phi 2 becomes high. From this point to this point, from this time to this time, both phi 1 and phi 2 are 0. Phi 1 and phi 2 is 0 means this is off and this is off. Whatever potential is there, that will be held because of the, that the capacitive thing, storage. And then at this instant, what is happening? Phi 2 is on for a short time. So naturally, the charge sharing will take place, and that will give rise to a small. Sorry, I'm sorry. That will give rise to a small fall, and then again at this instant of time when phi 1 is high. Phi 1 is high means again when phi 1 is high means you see that phi 1 is high means this potential is both of them have gone up, and at the same time A has increased. A has made a low to high transition, so this transistor is on. So naturally, as a result, both the transistors are now on, and this will again rise to the full voltage. And this will continue till the end of phi 1 pulse, because after the phi 1 plus this transistor gets off, naturally what will happen? It should go down because A remains high. At this instant, A is high. A is high means this transistor is on. When phi 1 is 0 and A is high means this transistor is on. So whatever voltage will there will drop. That is why it has happened. Then you see that you go on checking up to this instant. Then what is happening when? At this instant of time, phi 2, nothing is going to happen, because if this is zero potential, if the potential, there is no charge at this node, whether it is on or off does not matter. Of course, it depends on the earlier state. Normally, it will be like this, that everything here depends on this point. It does not have an independent supply. Please remember, the B dash point does not have any independent path of supply. Whatever charge comes here, so naturally, you see that is why, what you see that at this point, the 0 state will be retained. Even after this instant, there cannot be any change in the 0 state. You have to wait till this instant, when phi 1 comes. Again, for a short time, this is high, and it goes till you see that A is high. So again it falls. After the short clock duration of the phi 1 pulse, only for that time it is on. But then again, it goes to 0, because A is high, A is kept still high, then this transistor is on. Please remember this. And that's how, what is this called? Do you know what is this called? It's called a glitch. Glitch. Because normally this has got a very small duration compared to the overall pulse. That is the basic requirement of a good logic, clock logic, that the clock duration is small compared to the clock pulse period, clock period. That is very important. So these glitches usually will be of very short duration, and usually they do not cause any problem. But in very high frequency circuits, the glitches may cause problem, and we have to see that how to avoid glitches. Normally these glitches do not pose any problem for ordinary circuits. That has to be remembered. Then you can, in the same way, you can go on drawing the B. You just complete yourself. You come to this point. This again it rises. Then I think this rise will continue up to. A is high, but again phi 1 is high. That is to be understood. Even A is high, because phi 1, this is never 0. Please remember this. That is the novelty of this. A is high, but simultaneously phi 1 is also high. So it does not get a ground path. So it is maintained. In the earlier case, when A was high, B, whether phi 1 goes high or low does not matter. This node potential will be 0. Because phi 1, this point was grounded in the earlier case.
So even that clock will become low. That clock, A will become low.
Now you just see, at this instant what is going to happen?
So not that side. Waveform A, sir.
Acha, waveform A, I have made a mistake, you are saying. Let me see. Oh, acha, there is a mistake. Sorry. I'm sorry. This I have not seen. You are right. Yeah. Because this is now 0. Yes, you are right. এখানটা একটা ভুল করেছিলাম, then at this instant again you are right. Then at this instant what is going to happen? This will maintain because it is 0. That was a mistake I made. That was a mistake I made. Okay. Then at this instant, then what is going to happen now? Just has see. At this particular instant, there is a glitch here. Then when I come to this point, at phi 2 point, what is going? This is still 0, no problem. When I come to phi 1, you see that whether A is high or low does not matter, it will rise. It will rise. And then it will continue up to this point, sorry. It will continue up to this point. Then at this point there will be a charge sharing. Charge sharing. This will continue up to this point. Up to this point. And then what is going to happen now? It will rise. And then this is, yeah, it will rise. I have to wait till this point. You are right. Then again now it should down. It should, what should have happened here? This is rising here. Then at this instant of time, that should fall naturally. Then it comes up to this, and again high. It should fall like this. This will be like this. All right? Is it all right? At this point again, because now A is high and you see that phi 1 is 0, it must fall to 0. So there will be a number of small kinks, 1, 2, 3, 4, during this period, and a glitch at this instant. In the same way, you can go to the C point. Do you think that at this B dash point there will be some problem of these kinks, etc.? At a point B dash? So B to B dash drawing is very similar. You can draw it yourself. B to B dash, from B to exactly the way you have drawn A from input, you can also draw the potential at B dash from as if it is the input. In the same way, in synchronization with the clock phi 2, and finally you can come to the point C. Finally you can come to the point C. What you'll observe in this case, that I don't have time, what you'll observe in this case, that in this particular situation, otherwise it is working fine, excepting for the presence of some glitches which are not observed in the earlier case. You'll find that if you go on in the same way, you can now plot B dashed. You can draw the timing diagram of B dashed. You can also draw the timing diagram at C dashed. You'll find that it is very similar to the earlier case, but excepting for the presence of these glitches. Some glitches will appear and they cannot be avoided. And for reducing glitches, only thing, as rightly pointed out by some of you, I have to see that the clock duration is as small, as minimum as possible. So that has to be decided accordingly. For the earlier cases, clock duration was not that important. For the earlier cases, where I have not used such ratio-less logic, the clock duration was not that important. It should be above a certain value. But in this case, the clock duration should not exceed again a certain value. It should be between a minimum and a maximum. Otherwise, your circuit will malfunction. Now, as compared to the earlier case, therefore, can I just summarize that what are the relative merits and demerits of this? What are the relative merits and demerits of this? Can I summarize? Ratio-less, ratio-less design, and therefore higher packing density. But is it 100% right? Do you think that this is really a fact that you will get a very high packing density here? Here also please note, I have to maintain the capacitance at this node very large compared to the capacitance at this node, and so on and so forth. Otherwise it will not, these kinks will be too large. In order to reduce the kink heights here, I have to maintain the capacitance at the node B very large compared to the capacitance at node B dash. So what I have to do for that? I have to make this transistor much bigger than this transistor. These transistors much bigger than the past transistors. Again the same problem. But anyway, one can show here that you don't have to maintain that much high ratio in this case. You can, or sometimes what you do, we put some extra additional MOS capacitance at this point by some, you can put a capacitance here, extra MOS capacitance at the points B, C, etc. In addition, you can keep the MOSFET same size. Only things at this point in the circuit you keep some extra MOS capacitance. That will give rise to a little bit less packing density. But anyway, this will be better. From packing density point of view, ratio-less design is much better. Then, is there any other good features about it? Do you think that supply is not there? It is one bad thing, in fact, you should become good. Is there any good thing? Do you think there will be any advantages from speed point of view? Or power dissipation? Power dissipation will be much less. Much less. Then power on speed?
Speed is less.
How do you say the speed will be less?
The same.
Yeah, we don't really get much benefits from speed point of view as compared to HMOS, depletion mode load case. As compared to the depletion mode load case, we don't really get much speed advantage here. But otherwise, it will be much better than the saturated load case. Inverters with saturated load, it will be much better than that. And any fourth advantage? First advantage you have noted, higher packing density. Second advantage, much lower power dissipation. And third advantage, or more or less you can say, at least you can maintain a good speed. You can say that. You can maintain a good speed. I don't think there is any other advantage. But is there any disadvantage? One very important disadvantage, this is all plus points, minus points are glitches. And clock, that the entire responsibility of powering these switches goes to clocks. The clock generator, if it is a usual clock generator, that as it goes down the circuit chip, because the clock generator from clock generator, the power lines are coming. As it goes down, the clock will be deshaped because of the very high loading on the clock. So what is to, there should be some distributed buffer for the clock generator. In the circuit over the chip, there must be some buffer circuits at different locations. Buffers for, so that buffer means power amplifiers at different locations, so that the clock shape is maintained, clock height is maintained. This is called distributed buffers. Yes, therefore you see that, yeah, there are advantages, there are disadvantages too. And summing up, we shall try to make some summing up afterward. You will find that, yeah, relative, it depends on applications. In certain applications, we find the ratio-less is better. In certain other applications, we find the ratio design is better. Thank you.